So let's talk about quadratic equations. In a moment, I'm going to show actually the general form of a quadratic equation. But before we do, I'm just want to mention the things that we will talk about in this lecture. We're going to start by zero factor property, then we're going to look at the square root property, followed by completing the square and the quadratic formula. So again, before we actually look at the form of a quadratic equation, let's talk about this zero factor property. The zero factor property goes like this. Suppose we have two factors, a times b equal to 0. Now a and b themselves are real numbers. Okay, then they could be complex numbers also. So let's say if a times b equal to 0, and I'm going to allow for complex numbers. A and b are complex. Remember, real numbers are subsets of complex numbers. So if it works for complex numbers, it's got to work for real numbers. So suppose we have a product of two numbers that's equal to 0. So if the product of two numbers equal to 0, then for sure, at least one of them, if not both, has to be 0, correct? Then first one could be 0, or the second number could be 0, or both of them could be 0. So that's all the zero factor property is. Now the zero factor property seems simple, but it's actually going to help us solve equations. The keyword in the zero factor property is a factor. So that's why we emphasize so much on factoring. In order to solve equations, we need to have equations in factored form for this very reason, so we can apply the zero factor property to them. Okay, so having talked about it, and we'll see illustration of the zero factor property in just a few minutes here. So let's start by talking about the square root property. Oh, the general form. This would be the standard form, or the general form of the quadratic equations. The quadratic equation is going to be in the form ax squared plus bx plus c equals 0. Notice a quadratic equation is a second degree equation because the exponent or the power on x, the highest power, is 2. So this is what we call a second degree equation as well. Now what are the a, b, c? I already put here. A cannot be 0 because if a is 0, then we simply don't have that front term, and the equation reduces to a linear equation. We want to maintain the standard form of the quadratic equation by letting a to be different than 0. Now a, b, c here, the coefficients, again, it could be anything. For us, we're gonna start by allowing them to be real numbers, but they could be complex numbers too. So there we have it. Now remember this funny looking R, that means the set of real numbers. Now we were interested in solving the second degree or quadratic equations. So our first method, again preferred method, would be this factoring method, so we can apply the zero factor principle. So for instance, let's say I have an equation 6x squared plus 7x equal 3. Okay, and I want to solve this one. So we're going to bring the 3 to the other side, becomes -3. What's important, by the way, in the zero factor property or principle here is this 0. Aside from being factored, you gotta have 0 on the right side. Only product of two numbers equals 0. One of them has to be 0, or both. If I told you the product of two numbers is 1,000, then one of them need not be 1,000, right? It could be 40 times 25. It could be 50 times 20. So it doesn't necessarily have to be 1,000, one of them. So keep in mind, 0 is very important in the zero factor property. Now if you go through our factoring method here, let's say the factored form of this is going to be 3x, and I'm going to go first term 2x. That's how I get 6x squared. negative 3. Let me go negative 3 with this combination and see what happens. Now remember to check the factoring. Let's see if we have it right. We need to do the OI. This is the F, this is the O and the I. The O and the I, 3 times 3 is 9. Negative 2x is 7x, the middle term. Yes, this will work. So this is going to be the factored form. Now once we have the factored form, we can apply the zero factor property. This is in the form of a times b equals 0. So either the first one or the second factor must be 0. So I can write 3x minus 1 is 0, or 2x plus 3 is 0. Subtract 3, divide by 2, and we pick up a solution here. Add 1 divided by 3 for the other one, we pick up another solution. So there are 2 solutions in this equation. And here's a solution set made up of 2 numbers. So again, if we can factor, if it's factorable, the quadratic expression there, that's my personal preferred method. But what if it's not factorable? Well, if it's not factorable, and we're talking about integer factors, by the way. As I mentioned, every quadratic equation is factorable. It's just we're looking for integer values or whole numbers, natural numbers. We don't care about complex numbers, radicals, things like that when we factor. So there you go, factoring first and foremost. Now let's take a look at our next method for solving quadratic equations, namely we're going to go square root property. With the square root property, it goes like this. If x squared is equal to k, and here k is a constant, by the way, constant, then x would be plus minus square root of k. So in a way, it's as if we took the square root of both sides. That's what's called the square root property. Now, let's see if how does this come about. If I have an equation x squared equal k, I can move k to the other side, and that means x squared minus k is 0. And we can rewrite k in the form of square root of k squared, right? That's still k. That's just an alternate form of k. Now you recognize here we have difference of 2 squares, right? So we can apply the factoring formula, special factor formula for difference of 2 squares. It's going to be x minus square root of k and x plus root k equal to 0. And then by zero factored property, each of those factors could be 0. So from the first one, if I set that equal to 0, move root k to the other side, there's one solution. The second binomial factor, if I move square root of k to the other side, I'll get negative root k. And of course, there is a solution set. And that's what this property tells us. So that's the derivation of the property. Now, in order to be able to use this square root property, it does require that we have the square on x. Now, although we have a single variable here, x, one term x, but x could actually be an algebraic expression. So for example, let me do a simple example first. If x squared is equal to 25, according to the square root property, when I take the square root of both sides, I have plus or minus. Do not forget plus or minus when you take the square root of the constant. 25, so the answer are 5 and negative 5. So that's a simple application. Another example, this time I have x plus 5 squared is equal to 4. Notice I don't have just a single x, I actually have an expression. And this becomes x plus 5 equals plus or minus square root of 4. And the next step, x plus 5 is equal plus minus 2. And if I subtract 5 from both sides, So once I'm going to do negative 5 plus 2, another, call it first x, second x is going to be negative 5 minus 2, negative 7, and that's negative 3. And there you have this one. So again, the square root property does require, though, that the variable, whether it's a single x or x with another term, be in the squared form. So when we take the square root, we get that expression out of a squared form. Alrighty. Now, the role that k plays here, let me just put some facts about k. If k is positive, such as the example I have here, 25. If k is positive, then both solutions are going to be real. If that, then solutions, let me just say both solutions are real, such as, again, the example directly above. What if k is negative? If k is negative, then we're going to have two imaginary solutions. Then both solutions are complex, because we end up taking square root of negative numbers, right? If k is negative. What if k is 0? Well, then in that case, if k is 0, then in this case, 0 will be a solution. 0, and we call that a double solution. Double solution. Part of the reason is this. Let's say x squared is equal to 0. I can write it as product of x times x equals 0 and use the zero factor principle or property. Then the first x 0, second x is 0, and there you go. We have identical solutions here. They end up being the same, so for that reason, we only count the 0 once. That's the reason for calling it a double solution. Okay, and there we have this one. Now let's take a look at our next method. We're going to talk about completing the square method. Now, before we talk about completing the square method, let's talk about something different that's related to what we're about to do. I'm going to make a couple of binomials here. Suppose I have x plus 7 squared. If we square this, either by setting it up as FOIL or using the special product that we learned in factoring review, we're going to get x squared plus the OI is going to give us 14x, and 7 by 7 makes 49. Or we could just use a formula, right? First one squared, twice first by second, second one squared. Okay, so there we have that one. Let's do another one. Suppose I have x minus 5 squared. Then I'll tell you why I'm doing this. So that's x squared. Twice first by second is negative 10x. And negative 5 squared is plus 25. Okay. Now remember these trinomials, both of these and this one. Both of these trinomials, we call them perfect square trinomial. Perfect square. And the reason it's called perfect square again is because you can imagine a square of side x minus 5 by x minus 5. In that sense, that is that's where the perfect comes from. Okay. Now, let's actually take this the other way now. Suppose, well, let's do this. Let's again go back and look at the relationship between 14, 49, and 7. 7 is half of 14, right? Okay, half 14 is 7. Okay, 49 is when we square 7. So half of 14, and then we square to get 49, the constant. All right, that's just interesting observation. Cool. Let's take a look at the next perfect square. Let's try this one. Now, half of negative 10 is negative 5. And when we square negative 5, we get 25. That would be the constant here. All right. Now, why am I doing this? Well, suppose that I'm given a trinomial, and let's say this trinomial is going to be x squared plus 8x. Now, I'm holding off on the constant. The reason is because I want to know what constant should I add in order to have a perfect square trinomial. So if you will, there you go. What should that constant be? So I have x plus something squared. There, that's what I like to write it as. Now going back to the relationship that we just established with x plus 7 squared and x minus 5 squared. For the expression that I have, for this to be a perfect square trinomial, the number that goes in here inside the binomial, that number, remember, has to be 1/2 the coefficient on middle term, the x, namely 1/2 of 8. So half of 8 is 4. That's what's going to go in here. Now, as far as the constant in my perfect square trinomial, remember we have to square it. 7 squared here became 49. And that's what the constant was up there. We'll do the same thing. We're going to square the 4. Okay, so 4 squared is 16. And it looks like that's what's going to be here. And now we have a perfect square trinomial. And there you have it. Now, there is another justification for the name completing the square method. Let's look at the geometrical interpretation of this. Let's say I have a geometrical shape here. Okay. Looking at x squared plus x, we can think of x squared plus x geometrically as a square of size x by x. And then if I look at this little piece here, that is 4, and let's make this one also 4. So notice right now I have this geometric shape that's made up of a square and 2 rectangles. All right, so x times x would be x squared. That's the first term. Now if I look at the area of the rectangle to the side, length times width. Well, width is 4 and length is x. So the area of this rectangle is 4x. And if this is a rectangle whose side is 4, and then the width would be exactly the same as what's up here, right? That would be x also. And this area is going to be 4x as well. So the total area of this shape, whatever the shape is going to be x squared, that's this part, and then plus 8x. That would be the sum of these two regions, right? Now, if you look at this corner piece that's missing right in here, if I could add this piece, notice what we do, what we will have in turn would be a perfect square, right? So in this sense, what I'm doing now is I would like to complete this shape. So it's right now it's an incomplete square, isn't it? The way it looks. So let's complete this square, and hence the name completing the square method. So this little piece that we're going to add in order to complete and turn this into a full square is going to be 4 by 4, 16 plus 16. And now what I have is a square of side x plus 4 by x plus 4. And there's my perfect square, right? And x plus 4 times x plus 4 would be x plus 4 squared. So that would be a geometric interpretation of what I have up here. So you may have seen this in algebra classes, but it'll be interesting to see why they name the method the way they do. Now, one thing that's important for this process that I explained, how this became a perfect square trinomial, and the relationship between the number in parentheses and then the middle term and the number constant in the perfect square trinomial version. For this to work, the coefficient on x squared has to be 1. This number in front of x squared has to be 1 for this to work the way we explained it. So what if the coefficient is different than 1? We'll look at that in a moment. But let's actually take a look at an example here where we want to solve an equation. Let's say this one is x squared minus 4x minus 14. We're going to solve this by completing the square method. Completing the square method. So how are we going to do this? Well, for one thing, we need to move the constant to the other side. We don't want 14. We're going to create our own constant, right? We need to create a perfect square trinomial. And remember how this went. We're going to go half of the coefficient on x, half of this number. And that's going to be -2. And then we need to square it, right? Square it, and that becomes 4. Therefore, I'm going to add 4 to the left. Now, because this is equation, by addition property of equations, you have to add it. Whatever you add to both sides. Whatever you divide both sides by that. So there you have it. So on the right side, now we have 18. And to the left, this is a perfect square trinomial. It's going to be x minus 2 squared. Remember this number, the negative half of the coefficient on x, that's what goes in here. Okay, and there we have it. Now we can actually apply the square root property. Let's take the square root of both sides, and when we do, we get x minus 2. Don't forget the plus or minus square root of 18. Now square root of 18 on the side here, that's going to be product of 9 times 2, which we can think of as the square root of 9 times the square root of 2, makes it 3 rad 2. Let's add 2 to both sides to solve this equation, and I'm going to rewrite the square root of 18 as 3 root 2, the way we just showed it to be. And there you have it. So there are 2 solutions again. In this case, the plus minus, we often write it like this, but this is what it really means. One solution is that, another solution is this one. There's your solution set. Now, we don't need a calculator. Notice I haven't used calculator yet in any of my lectures, hardly at all, because the way we work with the numbers, we worked with numbers that turn out just fine without a calculator. So, again, the coefficient on x squared here was 1, and no problem, everything worked out as we expected it to. Now, what if that coefficient is not 1? So suppose now I have something like 3x squared, let's go negative 4x, and then plus 3 equals 0. Suppose we want to solve this one. First and foremost, the coefficient on x squared has to be a 1. It's a 3. So we do need to remedy this. And the corrective step is to divide everything by 3. Even on both sides, remember, we don't just divide one side, we divide both sides or multiply both sides by any number other than 0. And this equation becomes x squared negative 4/3 x plus 1 equals 0 divided by any non-zero is 0 on the other side. And now we got this important coefficient of 1 in front of x squared. Now, what do we need to do next? Well, just like we did in the one above, we don't want the number that's in that spot, 1 on that side. We move the number to the other side, and we create our own number. What is the number we want to create? Remember, it's going to be half of the coefficient on x, half of negative 4/3, and then squared. Half of negative 4/3, all the 2's divide out, so that's negative 2/3. Squared, that's going to be 4/9. Now half of the number, that negative 2/3, that's going to be inside the binomial. Half the coefficient goes inside the binomial. Don't forget to square it right here. The most common error is to leave the square out. Okay, if you do, that's just incorrect. So the square root property will not work appropriately like it should. So it does have to be square. And we're going to add 4/9 on this side plus 4/9 on the other side. Okay, and note we have a perfect square trinomial because the way that number 4/9 was added on that side. And on the right side, we have -1 plus 4/9. -1 is -9/9 plus 4/9. That's going to be -5/9. And here's x minus 2/3 squared. And now the square root property kicks in. Let's take the square root of both sides. And when we do not forget, anytime you use the square root property, you're going to have plus or minus here. Okay, so we're going to have plus minus square root of -5/9. Then we can break this radical into two parts, -5 over square root of 9. The quotient property works as long as one of these square roots is going to be real. Notice square root of -5 is not real, but the square root of 9 is, so I'm allowed to do this. And this is going to be x minus 2/3 equals plus or minus √5. Remember, square root of negative numbers, we use imaginary unit I to take the negative outside. And that would be √5i, and just to recall, I is the square root of -1. And now I can add 2/3 to both sides, plus or minus √5 over 3, and then put I in front of the fraction line. And there we have two complex solutions in this case. All right, so that's the gist of completing the square method. Now our next method is going to be using quadratic formula. And before, just to give you the quadratic formula, let's kind of derive the quadratic formula. It's kind of cool to see how it develops, where it comes from. You're not responsible for the derivation, so just kind of watch as this unfolds, how we come up with that equation that ultimately we're going to be using. So let's say I have a quadratic equation, ax squared plus bx plus c equals 0. And of course, a here could be any real number. All right, and cannot be 0. Now notice I'm allowing a to be a real number, means it could be positive or negative. So before we can apply completing the square method, because that's what I want to do, I want to make sure the coefficient on x squared is 1. Therefore, I need to divide everything throughout on both sides by a. Now, as we divide the left side by a, we're going to get x squared plus b over ax plus c over a equals 0. And then let's move c over a on the other side. Remember, that's the constant that we don't want on the same side. We're going to create our own constant. Now, what do we want to create here? Remember, what we want to create is 1/2 coefficient on x, which is b over a. Half of b over a, and then we square it. Now, half b over a is going to be the term in the binomial, right? The second term in our binomial. Therefore, I'm going to add, half of b over a squared becomes b squared over 4a squared. So I'm going to go b squared over 4a squared here plus b squared over 4a squared here. Now, because the way this b squared over 4a squared, this is the way. Because the way it was added, we know we have a perfect square trinomial on the left side. True? The square form of that is going to be x plus, always what's in the bracket goes here. b over 2a quantity squared. Alright, so that's the binomial form. And on the right side, we're going to have, whatever these two are, we can combine them. Now to combine these, let me move b squared 4a squared a little bit to the side, plus b squared over 4a squared. Now, because we have two fractions on the right side, okay, in order to combine fractions, we gotta have a common denominator, which we don't at the moment. So what needs to happen is I need to multiply by 4a, that first fraction. Now they have a common denominator of 4a squared. Let's write the common, and I'm going to write this as b squared minus 4ac. I just wrote b squared first, followed by the first fraction. So I wrote the second fraction first, first fraction second. We can do that because addition is commutative. Perfect. Next step, we're going to take the square root of both sides. Now, when we take the square root of the left side, we just have x plus b over 2a. On the right side, we're going to have plus or minus. And then we have a square root at the top, b squared minus 4ac, which probably looks familiar to most of you. And in the denominator, though, we have square root of 4a squared. All right. Now, let's look at the square root of 4a squared here. Remember, I allow a to be any number. So that's going to be 2, square root of 4 is 2, and then square root of a squared. And square root of a squared, if a is allowed to be any real number, it's going to be absolute value of a, because remember, the radical symbol means principal or positive root of that number. So in order to guarantee we have a positive principal root, I need to have absolute value of a here. X plus b over 2a is equal to, so I'm going to write this as plus minus the numerator minus 4ac over 2 absolute value of a. Now, you probably have not seen it in this form, but we're not done yet. Now, let's take a look at our absolute value of a. Again, by definition of absolute value, if a is positive, or a greater than or equals 0, we simply write a. Whatever this is, we just write it out for the answer. But if a is negative, we need to put a negative in front of a. For example, remember absolute value of negative 5, I cannot say that's negative 5. This is my a. There is a. See, it won't work because it has to be positive. Therefore, we put negative in front of it. So now it's negative of a, which results in a positive answer. So that's the rationale for writing this piece. Now, I can actually write this denominator absolute value in two parts, and when a is positive and when a is negative. So x plus b over 2a, in other words, will equal to plus or minus b squared minus 4ac divided by 2a. That's the case where a is positive. Or is x plus b over 2a equal plus or minus the numerator over negative 2a, that's when a is negative. See, I'm following this rule. All right, now let's proceed. For the first one, I'm going to subtract b over 2a plus or minus, and then we have square root of b squared minus 4ac divided by 2a. And then when we combine this with the common denominator, that's just negative b plus or minus square root b squared minus 4ac. So here's the first part of the quadratic formula. Now let's carry this one over. I'm going to do the same thing, subtract b over 2a from both sides. Now, in here, you see, I have plus minus, and then I have negative in the denominator, true? So I'm going to make that minus plus. The reason is this, with plus minus, and the negative in the denominator. Remember, plus minus means you have two answers here. If you look at plus, positive over negative is negative. If you look at the minus, negative divided by negative in the denominator yields a positive answer. So the plus minus divided by negative in the denominator actually switches plus minus to minus plus. That's why I have minus plus. But then minus plus, it's really the same thing as the other one, right? Let me show you what I mean. Here's what I mean. Let's say I have plus or minus 5. Isn't that the same as minus plus 5? Plus minus 5 means 5, negative 5. Negative 5 plus 5 means negative 5 and 5 also. So they're the same. Isn't that cool? It's playing around with plus minuses here. So, as a result, I can rewrite minus plus as plus minus. And when we do, we get exactly the same thing. So these are really the same. And for that reason, quadratic formula works whether the coefficient on x squared is positive or negative. We use the same formula. All right, now what are you responsible for? Ultimately, this is it. Know this. There you go. That's the one we want to learn about. They're both the same again, but that's the one that's often in textbooks. Now with quadratic formulas, it's really like using a canned food. You just open the can, maybe heat it up in the microwave or something, or just eat it right out of the can. The quadratic formula, we just use it to solve the equations, right? There's no step to show, and we don't have any in-between steps. It jumps right to the conclusion. It says the answer is this. So let's see how we're going to use this. Suppose I have 2x squared equal x minus 4. So in order to use quadratic formula, however, I got to be careful. You identify the ABC when you have a 0 on this side. So if I say my constant is negative 4, that's an error. That's not C, the constant. Constant is actually 4. Remember, it has to be 0. So let's identify our ABCs. A is 2, B negative 1, and C is 4. The ABCs, here's A, B, and C. Remember, those are the numbers before the variable, and C the constant. And once we identify the ABCs correctly, we can solve the quadratic equation using quadratic formula. Let me just echo the formula one more time. B squared minus 4ac and divided by 2a. Now negative b would be negative 1 plus or minus b squared, that's negative 1 squared, minus 4. A is 2 and C is 4. All of that divided by 2 times 2. You see, there are no steps to show. It's just a matter of plugging in for ABCs. And if we do it correctly, then we just have to be able to do the arithmetic just with numbers. Negative 1 in the numerator, that's 1, plus or minus. The radicand is going to be negative 1 squared. 4 times 2 times 4 is 32. Negative. Divide by 2 is 4. So that's 1 plus or minus square root of negative 31. Divide by 4. Now anytime we have square root of negative numbers, remember the I we write it as 31i in order to get the negative radicand and out, the negative out of the radicand. That's the legal way of doing it. And there we go. We have two solutions. One answer is 1/4. The other one is square root of 31 divided by 4i. And please note the most common mistake here is to write it as 1/4 plus minus root 31i. This is wrong, because the 1 and root 31, both terms divide by 4, not just one of them. Both terms in the numerator do. All right, and there we have two complex solutions. All right, hopefully you follow this one. Let's try another example. In our next example, I'm going to do x cubed plus 8 equals 0. Now this one we recognize as sum of two cubes. Okay, and we have a special factoring formula. Let me recall the formula in this form. A cubed plus b cubed. We write it as a plus b, first one squared, negative first by second plus second one squared. So let's try this one. Here is a plus b, first one squared, negative first by second plus second one squared. So we have a linear factor and a quadratic factor. Now, by zero factor principle, the linear factor could be 0 or the quadratic factor may be 0. And here subtract 2. We get one solution out of the linear factor, first degree. Now this one is not going to be factorable, remember? The quadratic we get is not going to be factorable. And again, I want to emphasize, we can factor any quadratic. The reason we say not factorable is because we're looking for integer factors. Let me emphasize that. We're looking at integer factors. That means we don't want fractions, radicals, complex numbers, imaginary numbers like that. All right. So this one, I won't even bother setting it up like this. Remember that work? Foil. We're not even going to do that. Just going to use quadratic formula. A is 1, B negative 2, and C is 4. So the solution to the quadratic equation portion of this equation is going to be negative b plus or minus b squared minus 4ac divided by 2a, and remember a is 1. Next step, 2 times 1 in the denominator, that's 2, double negative on 2 on top, that's 2 also, plus or minus. The radicand, 2 squared, negative 2 squared, 4. 4 times 1 times 4 is 16. So this is going to be 2 plus or minus square root of negative 12 divided by 2. Now, square root of negative 12. Again, root negative 12. We can write this as 4 times 3 times negative 1. Square root of 4 is 2. 3 remains in the radicand, and negative 1, square root of negative 1, that becomes the I, the imaginary unit. So the answer is 2 divided by 2 plus or minus 2 root 3 right in here. That was square root of 12. 2 root 3 divided by 2, and here is the I. And if you cancel the 2's, we finally get the reduced version of our answer. So we do have 2 complex solutions for this one. All right, and let's see, hopefully I did this one. I just want to check on my 16:4. Yeah, that looks good. So the answer is going to be 1 plus minus root 3i. Now, let's finish this part by talking about discriminant. Discriminant of a quadratic equation. So the quadratic equation ax squared bx plus c equals 0. The part in the quadratic formula, if you go back to a quadratic formula, this part of the quadratic formula was under the radical sign only, the b squared minus 4ac. It's called discriminant d, right, which appears under the radical sign. Now, depending on whether the discriminant is positive, negative, or 0, we can look at the nature of solutions to quadratic equation, kind of get an idea of what we're expecting, what should happen when we solve the equation. In fact, I can write the quadratic formula in terms of discriminant in this form. There you go, discriminant over 2a. So finding discriminant isn't a waste of time because we have to do it in the formula anyhow. Now, what if d is 0? We're going to look at three possibilities. d 0, d positive, d negative. Well, if d is 0, then x is going to be simply negative b over 2a, isn't it? Because the square root of 0 is 0. And plus minus 0 is 0. Therefore, the solution is going to be x equal negative b over 2a. And this would be what we call a rational real number, a rational solution. And here's a case where we have, again, what we call a double root. Because this is, again, the second degree equation, so we have a double root. If the discriminant is negative, well, square root of d will be negative, right? Well, d is negative, so square root of d won't be negative. I mean, d will be negative, so square root of d would be imaginary if d is less than 0. And therefore, what are we going to have in the way of solution? There will be two complex, and by complex here truly we mean non-real, two complex solutions. Okay, and finally, if the discriminant is positive, and by the way, we have the example of discriminant negative. Remember, discriminant was negative. Look at the solution. We have two complex, distinct complex solutions. And by the way, these two complex solutions, they will be conjugates. That you will see them again up here. The solution 1 plus root 3i and 1 minus root 3i. These are complex conjugate of each other. Now, what if the discriminant is positive? We did one, I think. No, we haven't yet. But if it's positive, then discriminant positive, that means we're not going to run into imaginary situation, right? In that case, it depends whether we can take the square root of that positive number as a perfect square or not. So if d is perfect square, then we will have two rational solutions. And if d is not perfect square, then we're going to have two irrational solutions. So here's a case, for instance, I have square root of 16 plus minus. That becomes plus minus 4, and that's the case of rational because 16 is perfect square. Remember, your perfect squares are 1, 2 squared, 3 squared, 4 squared, 5 squared, and so on. So if your radicand is any one of these perfect squares, then you have two rational. If the radicand is positive non-perfect squared, like 11, so that's not perfect square, so square root of non-perfect square numbers would be irrational. And that's the reason for having two irrational solutions. Let me write this for some, you need to see it. And that's the full word, irrational. And there we have it. Now, let's take a look at some examples here together. And we just want to solve a bunch of quadratic equations so we can get practice with it. X squared negative 5x plus 6 equals 0. Okay, so for this one, let's say we want to solve this by zero factor principle. So that means I need to factor it. Remember, preferred method is factoring. The product is 6 positive, middle term negative, so both numbers will be negative. See how clean that is? Factoring really works well. First factor would be 0, or the second factor may be 0, from which we get our two solutions. And there we have that one. Nice, clean. Again, it worked out perfectly. We could have done this by a quadratic formula. We could have done it by a square root property. We could have done it by completing the square, which completing square invariably leads to square root method, because we get the square of a binomial and we have to take the square root of both sides. Now, another example. Let's say I want to do x squared minus 100 equals 0. This one again by factoring, that would be x minus 10, x plus 10 equals 0. So we get 10 or negative 10, two solutions. You could also do this by a square root property. Move 100 on the other side. Okay, so it becomes 100 positive, negative on the left, positive on the right, and then hit it with the square root property. Remember, with the square root property, you have plus or minus. So these are, again, the same results. Different procedures, but same outcome. Now let's try this one. We want to solve something like 3x minus 1 squared. I don't know, whatever number, doesn't matter. Let's make it 12. Now, because we have a square of a binomial, we go right to the square root property. I don't need to expand it, combine like terms, set it equals 0. That's just too much work, unnecessary work. So let's just take the square root of both sides. 3x minus 1 plus minus square root of 12. And square root of 12, if you think of 12 as product of 4 by 3, that's going to be 2 rad 3. So we have 3x minus 1 equal plus or minus 2 root 3. And 3x is equal to, add 1 to both sides, plus or minus 2 root 3. And finally divide by 3, correct? Let's divide both sides by 3. And that's going to be x is equal to 1 plus minus 2 root 3 divided by 3. And there we have our two solutions. Let's take a look at, how about, let me make another one up. This time, oh, we haven't done completing the square method. Let's do a completing the square method. All right. Now this, this one that I made up actually is factorable. I know it is. There you go, x minus 3, x minus 1. So here's the solution, falls right out. See how easy it is if it's factorable? But let's do this by completing the square method just to get practice. This number has to be 1, right? The coefficient on x squared must be 1 for the completing the square method to work. And it is, so we can proceed. We're going to keep the x terms, move the constant to the other side. And remember our routine, half of the coefficient, half of negative 4 squared is what we want to add. Half of the coefficient on the x, not x squared, but x. Half of negative 4, that's negative 2. That's going to be inside the binomial. In a moment, we are about to write it. So that's what we're going to put inside the binomial. It's going to be x minus 2 squared. The number we're going to add to both sides is 4 plus 4. And don't forget to add on this side. Cannot do it just to one side. 4 minus 3 on the right makes 1. And now we can, and also don't forget the square on the binomial. Now we can take the square root of both sides. That's the square root principle. And square root of 1 is 1, plus minus 1. We're going to add 2 to both sides. Another way we handle plus minus, once you add 2 plus 1, we get 3. Another, you take away 1 from 2, you get 1. Solution is 3, 1, just as it was up here. Again, I personally like factoring. This is much nicer, quicker, cleaner, and it looks better. But this is math, so there's always more than one way to do things, most cases. And there you have it, completing the square method. Now, what if the coefficient isn't? Let's do one where the coefficient isn't going to be 1. Okay, now, let's see. Let's take a look at this one. In this example, I'm going to make the coefficient different from 1. So let's make the coefficient not too big. Let's make it 2x squared plus x. I'm going to go ahead and put 10 on that side. Okay. So let's see. Before we can actually do this, remember the coefficient has to be a 1. Therefore, we must divide everything by 2. And go by 2, by 2, and by 2. This is going to become x squared plus 1/2 x equals 5. What do we add to both sides is 1/2 of this number, which is a half itself. So it's half of half squared. Half of half is 1/4. 1/4 squared is 1/16. Now 1/4 is what's going to be inside the binomial. But first I need to add 1/16 to both sides. So here's plus 1/16 plus 1/16. The perfect square trinomial is going to be square of a binomial. The 1/4 goes in here. So that's x plus 1/4 squared. And 5 plus 1/16. Let's do that one here. Give it a denominator of 1, 16, and need to get LCD, which is 16, multiply top bottom of 5 by 16. 5 times 16 is 80, plus 1 over 16, which is 81/16. So that's just going to be 81/16. That's just to get it in the form that's now ready for square root property. And now let's take this square root of both sides. We get x plus 1/4 equals plus or minus square root of 81/16. And that's going to work nicely because 81 is perfect square, so is 16. Next, I'm going to subtract 1/4 from both sides, or move a quarter to the right. Plus minus 9/4. This is going to be -1 plus or minus 9 divided by 4. So again, how does the plus minus work? Once we have -1, once it's going to be -1 plus 9/4, another is going to be -1 minus 9/4. -1 plus 9 is 8, 8/4, 2. -1 minus 9, -10/4. Divide the 2's out, we get 5/2. So this one has two solutions. The solution set is -5/2 and 2. And those are the solutions to this one. Okay, how about if we do a quadratic formula now? So in this next example, let's see, how about this quadratic? Something with coefficients not too large. Now remember, for quadratic formula, we just need to identify the ABCs correctly. Got to make sure the equation though is in standard form, right? It's got to be ax squared plus bx plus c and 0 on the right side. If not, we move everything on the left. Now we can identify the ABCs. For this exercise, a is 1, b is -1, and c is -1 also. Here's a, here's b, and here is c. Good. Now we can just go to our formula. The solution x is negative b, that's going to be negative of -1 plus minus b squared, that's -1 squared, minus 4a, and c is -1. Divided by 2a, that's 2 times 1. So double -1 is 1 plus or minus 1 squared, -1 squared is 1. 4 times 1 times -1 is -4, and the negative in front of 4 makes positive 4. So notice, by the way, let me write this as that our discriminant is positive, right? Discriminant positive and non-perfect square. So that means I would expect 2 irrational solutions. And we're looking at the 2 solutions right in here. You can split that into 2 parts as 1 plus root 5 over 2, 1 minus root 5. Let me show you what I mean instead of talking about it. Here's how you may see the answer, the variations. 1 plus root 5 over 2, 1 minus root 5 over 2. This is acceptable. Or you may see the answer in this form, 1/2 plus root 5 over 2, 1/2 minus root 5 over 2. That's also permissible. So here's 1, 2, 3 different ways of writing the answer. All 3 of them are correct. And that's solving the quadratic equation. Let's see. Let me do where we just have to identify the nature of solution. How's that? In this example, we don't want to solve. We just want to know what kind of equation, what kind of solutions we would expect. Okay. So we have to evaluate the discriminant, right? And then use it to determine the number of solutions and whether they are complex, rational, irrational, what have you. So we don't want to solve this. So A, B, and C. Make sure you have a 0. I drop the 0. Let's put a 0 here. This is a must. Okay, you gotta have that before you identify the ABC. So A is 1. There is A. B is -8. Correct? B is -8. And this is B. And C is 16. Cool. Now, our discriminant D, B squared minus 4AC. That's -8 squared minus 4A. C is 16. Okay, move that little away from the 0 for readability. There you go. Now, -8 squared, that would be 64. 4 times 16 would be 64. Oh, interesting. The discriminant is 0. So if the discriminant is 0, therefore we have 1 rational solution, right? 1 rational solution. And it's going to be a double solution. Okay. Now, let me again solve this just so you know what we mean by that. I can actually factor this one. X minus 4, x minus 4. Okay, product 16, sum -8. Now, when I solve this, first factor, x must be 4. Second factor, x must be 4 to be 0. So you can see why it's called one rational solution. The solution is 4. We don't count it twice. It is called double solution, as you can see, because there's 2 of them. But for our reporting purposes, we only report it as 4. But we acknowledge, we know that that's a double solution. All right, and let me do one last one here, and we'll be done with this lecture. Trying to keep the lectures on or about an hour. 9x squared plus 11x plus 4 equals 0. Again, here's A is 9, B 11, and C is 4. Discriminant D is going to be B squared minus 4AC. 11 squared is 121. 4 times 9, 36 times 4 is 144. Now 121 minus 144, that's going to be negative 23. So clearly that's negative, right? Therefore, if discriminant is negative, remember the kind of solution we get? We get 2 distinct non-real complex solutions. Distinct non-real complex solutions. So we get 2 imaginary solutions, in other words. Distinct here meaning different. They're not the same. See here? Up here, the one that I just did, those are not distinct. They're the same. 4 and 4. So we get 2 different. Then these 2 distinct, just so you remember, these will be conjugate. All right. And I think we are good. That's all I wanted to do in this section of our work. And again, hopefully you followed everything that we did. If not, please go back and review this. This was a long lecture. Go back and review this one. And as always, again, thank you for watching the video.